Hello everybody, and welcome back to another Big Ideas Algebra 2 lesson. Today, 9.2. So in this section, we're going to be talking about angles, we're going to be talking about angle measurements, and we're also going to talk about a different way to measure angles, with something called radians. Before we jump into these notes, I want to let you know we shouldn't be afraid of radians. It's just another type of measurement, like I can measure in feet or meters. So let's take a look. When we talk angles, we always want to talk about them in something called standard position. This is just to standardize the way we look at them, so we're all looking at the same angles with the same way of measuring it. Every angle has an initial side, which we put along the x-axis in the positive direction. The terminal side is the part of the angle that actually moves. So this terminal side, for instance, is right over here. The angle itself, then, is what is between the initial and the terminal. Again, we are graphing this on xy plane just to make it a little easier to keep track of. So if the vertex is at the origin and the initial side is on the positive x-axis, we're in standard position. When we measure an angle starting at 0 and going all the way around this way, we end up with a positive angle. If we're going clockwise, meaning we're going the other way around, we're going from 360 down. So like 360 to 270 to 180 to 90 to 0. We say that is going to be a negative angle. Just keep in mind, the terminal side could also rotate more than 360 degrees. For instance, maybe we make a full loop and then go to this position. So here we're asked to draw a couple of angles in these various positions. The first thing we should always do is to set up an x and y axis. We know that we want the initial side to be right here along the positive x-axis. But now we've got to start thinking, what would a 240 degree angle look like? My recommendation is this. We know that if we're starting at 0, a right angle, one that would go straight up and down, is 90 degrees. And if the angle was flat like this, it'd be at 180. And if it went 3/4 of the way around, it'd be a 270 degree angle. And if it went all the way around, it's a 360 degree. The first step is to recognize that 240 is in between 180 and 270. For those of you who remember your quadrants, this is in the third quadrant. So we know, no matter what, that our angle is going to go to 180 and probably beyond. But how far beyond? What we can do is we can take 240 and measure this, subtract this 180 degrees here. That'll tell us how much further than 180 degrees we have to go. So what's 240 minus 180? It's 60. So a 240 degree angle is just 60 degrees past 180. This is one way that we can draw our angles, is by starting off, getting to one of these axes, and then see how much further we need to go. What if I gave you an angle like 500 degrees? Well, our 4 axes here can only fit up to 360. So here's where we need to be creative. We know that an angle measure bigger than 360 degrees means that we did like a loop. So if this is our initial side, we know, at the very least, that we made a full rotation around. From 0 to 90 to 180 to 270 to 360. Well, how much further than 360 do we need to go? Again, we can use subtraction. 500 minus 360 is 140. So we should go 140 degrees past 360. So I'll go 90 more. And how much past 90 is 140? Well, I need 50 more degrees, so there we go. This angle here, then, is a 50 degree angle, and it's what finishes this drawing. Finally, what if we have a negative 50-degree angle? Well, now we're just sort of measuring backwards. We're starting at 360, and we're going 50 backwards. So, what's 50 less than 360? 310. So this is just the same as a 310-degree angle. We're just starting from our initial side, and we're going to 310, which is about here. There we go. So something interesting happened. With our middle case, we started talking about this 140-degree angle because we were able to do 500 minus a full rotation, which is 360, and that 140 was the rotation we had left to go. We call the angles 500 degrees and 140 degrees co-terminal because their terminal sides are in the same place. It's the same angle, one of them just went around once. So you can find an angle that's coterminal by adding or subtracting multiples of 360 degrees. Let's see an example here. Let's say we're starting with a negative 45-degree angle. And I wanted to find one positive angle that's coterminal to it and one negative angle that's coterminal to it. Well, to make a positive angle here, wouldn't I just have to add 360 degrees? What's negative 45 plus 360? That's going to be 315. So we would say that these two angles are coterminal, or that they end up with the same terminal spot. What if I wanted to go in the other direction? What if I wanted to make a negative one? Well, I could subtract 360, giving me a negative 405-degree angle. All three of these angles are coterminal with each other. Can you try to find two other coterminal angles from 395? One of them should be positive, and one should be negative. Pause the video and see if you can do it. Hopefully you recognized here that we can subtract 360 degrees to get to an angle of just 35 degrees. That's a positive coterminal angle. But we could go even further down. If we go further down into the negatives, subtracting another 360, what do we get? We would end up with a negative 325-degree angle, which is also coterminal. Very nice. Let's flip the page. So, when we talk about using radian measures, I'm going to explain what radians are in words here, but there is a very fantastic animation that I recommend you watch. The link is down in the description. Please watch that animation if you're having trouble wrapping your mind around what a radian really is. We can measure angles using these measurements called radians. So, a radian is the measure of an angle in standard position whose terminal side intercepts an arc of length r. Told you this definition was complicated. Watch that animation, it'll help you. But long story short, if we have a circle with a radius of, let's say, r. So here's my circle. In this case, I'm just going to make a radius of 3, just because it's nice to see. If I have this radius r, 1 radian is the amount of movement I need to do along the outside of the circle to also get to length r. The angle measured between the end of this arc and our original is the same measurement in radians. Radians would be the distance here. Degrees would be the angle. That's literally all it is. It's like measuring an angle inside of a circle comparing to the distance on the outside of a circle. Remember, the circumference of a circle, we learned this in middle school, is 2 times pi times the radius. Well, hang on a second. If the entire circumference is 2 pi r, and 1 radian is 1 radius, how many radians are there in a full circle? Wouldn't we just get rid of the r? There are 2 pi radians in a full circle. So that's about 6.28 radians. And no matter how big or small your circle is, the entire circle will take 6.28 radians, or 6.28 radii, to work your way around the outside. So we've actually got ways of converting between degrees and radians. One way to do so is to convert using a formula. The formula to convert from a degree into a radian is to multiply your angle measure by pi over 180. This is not something I recommend you use your calculator to do unless you are using your calculator to simplify the fraction. Use your simplification skills here. Do not give me a decimal. But let's see this. If I'm starting with a 120 degree angle, and I want to convert it to radians, the formula just says I should multiply by pi over 180 degrees. Well, this would end up giving me 120 pi over 180. And how do we simplify that? Well, we find the greatest common factor that both of these numbers can be divided by. If you wanted to work this out, you absolutely could. But I also want to show you a bit of a shortcut using your calculator, because your calculator can simplify fractions for you. If you're using the fraction function in your calculator and you click enter, it'll simplify it for you. This is 2/3, because both the top and bottom can be divided by 60. So we can rewrite this and simplify it as 2 pi over 3. Try the negative 20 on your own. See if you can convert that into radians. So again, the formula is multiply by pi over 180 degrees. This is going to give us negative 20 pi over 180. And what's negative 20 over 180 simplified to? Negative 2 over 18, sure, but if you simplify further, you could say that this is negative 1 over 9. This is just negative pi over 9. To go from a radian back to a degree is very similar. All we need to do is multiply by 180 over pi, the reciprocal. Why does this work? Well, because if there's a pi on top of the fraction and a pi on the bottom, don't they cancel out? So here we would just be left with negative 180 over 12, and that one actually divides very nicely. We end up getting 15 degrees, so negative 15 degrees. Can you try converting 5 pi over 4 radians into degrees? If we do this, we multiply by 180 over pi. The pi's cancel out on the top and bottom. So we're left with 5 times 180 divided by 4. 5 times 180 is 900, so it's 900 over 4. And what's 900 divided by 4? This will give us 225, so this is 225 degrees. Done. Remember what I said, radians are just another type of measurement. It's like Fahrenheit and Celsius. They both measure the same thing, just in different ways. Down here, there is a little bit of a diagram. And I handed out this diagram to everybody in person. We're actually going to talk about how to build or construct this diagram, because this is going to be something we're going to use in 9.3 as well. First things first, I want us to construct all the different angles here. So I'll tell you this. Every one of these angles follows the same pattern. 0 degrees, then it goes up to 30 degrees, then goes 15 higher to 45, 15 higher to 60, and 30 higher to get to 90. So take a moment to pause the video and see if you can fill out the rest of these angles following that same pattern. We go up 30, up 15, up 15, up 30, up 30, up 15, up 15, up 30. As we go through, we should see that we get 120 degrees, 135 degrees, 160 degrees, 150 degrees, messed that one up, and then 180 degrees. Down below, we get 210 degrees, 225 degrees, 240 degrees, then 270, and over here we end up getting 300, 315, 330, and 360. Cool? Cool. Now we want to convert these into radians. But instead of using the formula over and over again, we are going to think about this in terms of what part of the fraction each arc is making up. So, for starters, if you have 0 degrees, you also have 0 radians. There's no distance that you're traveling along the outside. And what was one full rotation around again? We said that was 2 pi. So what's halfway around? If halfway to 360 is 180 degrees, what's halfway to 2 pi? We can just divide 2 pi in half. That gives us pi. So 180 degrees is pi radians. Let's see if we can use this idea of cutting in half to help us out with some other parts. So let's look at the 90-degree angle. If 2 pi is here and pi is here, and we wanted to cut it in half again, that would give us 90, right? So pi cut in half is pi over 2. Cool. We can follow this pattern to even help us with the 45-degree angle. If we wanted to cut this angle in half again, well, 90 degrees halved is 45, but what's half of pi over 2? That we could write as pi over 4. Now, here's where I want to show you how we're going to construct the rest of this circle. And afterwards we'll do the 30s and 60s and all that. 1/4 of this half circle is pi over 4. In fact, I'm even going to draw the red line here just to show that we are talking about just the top half of this circle. This top half is pi, so if I cut it into 4 pieces, we get pi over 4. So this first section here is pi over 4 radians. If I go another quarter of the way around, well, then I'd have 2/4. So couldn't I write that as 2 pi over 4? 1 pi over 4 is a quarter, 2 pi over 4 is a half, which is why we simplified it to a half. Then what would happen if I went another quarter of the way around? Well, we went 1/4, 2 quarters. It makes sense this would be 3/4. So it's 3 pi over 4. We can actually use this to even go further. 1 pi over 4 is 1/4. 2 pi over 4 is 2/4. 3 pi over 4 is here. Pi is just the same as 4 pi over 4. That's why we write it as pi, because the 4's cancel out. And we can go even beyond this half circle now. We know that every one of these diagonal cuts, the ones that are perfectly diagonal like this, are going to be an extra quarter of the way around the circle. So all we need to do is just keep adding quarters. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Makes sense this one would be 5 pi over 4. And what's this one over here? Well, that's another quarter of the way around, so that's 6 pi over 4. But 6 pi over 4 can actually simplify. 6 over 4 simplifies to 3 over 2. So this is 3 pi over 2. We can go another quarter of the way around to get 7 pi over 4. That's the 315 degree angle. And of course, 2 pi would also be the same as 8 pi over 4. Cool. We were able to construct all these different radian measures without doing a single hint of formula. All we had to do was figure out what portion of the top semicircle we were covering. So can we use that same trick to help us with the 30 degree angle, for instance? Well, with this 30 degree angle, we see that it's certainly going a little bit, but it's not going very far. It's even less than a quarter of the way around. We just have to figure out how far that is. Well, if a full semicircle is 180 degrees, how much of that semicircle is 30 degrees? That's 1/6 of the way, because 30 times 6 is 180. That means that each of these is 1/6 of the semicircle. So this one here, this 120 degree angle, and this 150 degree angle. So we can count up in the same way. This is 1/6 of pi, so we call it pi over 6. This 60 degree angle here is 2 pi over 6, but that can be simplified. 2 pi over 6 simplifies to pi over 3. So this is pi over 3 radians. 3 pi over 6, but that's just 2 pi over 4 or pi over 2. So we already handled this one. That's 3/6. Here we have 4/6, which is 4 pi over 6. Again, that simplifies. 4 pi over 6 is the same as 2 pi over 3 when we simplify the fraction. Here we would have 5 pi over 6. And here, pi would be 6 pi over 6. We know we're right because the 6's cancel out and makes pi again. Can you count up by sixths to finish out this circle? Pause the video and see if you can. We end up getting 7 pi over 6. This one here is 8 pi over 6, but that reduces down to 4 pi over 3, or 4/3 pi. Here, the middle point would be 9 pi over 6, but we already simplified that to 3 pi over 2. This next one would be 10 pi over 6. That also, believe it or not, simplifies to 5/3, so 5 pi over 3. And last but not least, well, not even last, next we have 11 pi over 6. And now, last but not least, we have 12 pi over 6, which we know is just 2 pi. We've just figured out what these main angles are in radians. And if you know what they are in radians, you can very easily do calculations with them later. So this unit circle is going to be very helpful for us. Let's see if we can use it. If we're trying to convert from 135 degrees, we know that's on our unit circle. 135 is 3 pi over 4, so we can just write that down as 3 pi over 4. Now, negative 40 actually isn't on this, nor is its coterminal angle of 320. This is one where you would have to use the formula because, unfortunately, this one is not on our unit circle. You would end up with negative 2 pi over 9. We can go backwards from radians to degrees as well. So if we're starting with 5 pi over 4, we know that's a 225 degree angle. And if we have 7 pi over 6, according to this chart, 7 pi over 6 is 210 degrees. Very nice. Last but most certainly not least, we have ways of using these radians. So radians can be used to measure two specific things about a circle. One of them is called the sector. A sector of a circle is just a part of a circle's area. It's like this shaded portion of a circle. It can be as big or small as we need it to. Think of it like a slice of pizza. The the central angle of a sector is the angle that's formed by those two radii. So you're always going to have this angle here, and that's going to give you a sector. Now, there is something called the arc length. The arc length, S, is just your radius times your central angle theta measured in radians. This is why radians are useful, because it's a concrete measurement. Arc length is just S equals R times theta. The area of a sector is a bit tougher. It's this formula here, but this is one that I would give you. So let's take a look. A softball field forms a sector with the dimensions shown, and we want to find the length of the outfield fence and the area of the field. Well, first, we have this 90-degree right angle here, but we can't use it in its current form. We need to first turn it into radians. So, according to our chart, a 90-degree angle is the same as pi over 2 radians. So this angle measure, theta, equals pi over 2. We know the formula for arc length is S equals R times theta. Well, we know our theta now, it's pi over 2, and we know our radius. The field is 200 feet across. So it's just 200 times pi over 2. The arc length is going to equal 200 pi over 2, which is 100 pi. That means, in total, the outfield fence is made up of about 314 feet of fence, because pi is 3.14. Similarly, we can figure this out using the area. The area of the field is going to be 1/2 times your radius squared times theta, all of which we already know. We already know from the last part that our radius is 200, so it's 200 squared times pi over 2. Well, if we do these next couple steps, this is just simplification. 200 squared is 40,000 times pi over 2. I'm actually going to multiply the 1/2 times pi over 2 because it seems easier for me. That's just going to be pi over 4 times 40,000. And pi over 4 times 40,000 is 10,000 pi. Which means the area of the field is about 31,415 square feet. And we are done. Thank you so much for listening, everybody. Have a fantastic rest of your day. I'll catch you in the next one.